Hello, and welcome to this elementary statistics lesson on simple linear regression. In this lesson, you will learn the definition of simple linear regression, how to calculate a regression equation, and how to interpret a regression equation. Whereas correlation is not a measure of causal relationships, the statistical technique regression can be used for this purpose. Regression measures the extent to which the variation in independent variables causes the variation in dependent variables. The regression equation obtained is a function that describes the particular way in which the variation of the independent variables influences the values of the dependent variables. A particular type of regression, simple linear regression, is used in the situation in which one independent variable is influencing one dependent variable, the regression equation describing a straight line. A regression defines a line of best fit. That is, a line that minimizes the vertical distance of the data points from the line. These distances are called residuals. Regression is a form of inferential statistics. It's the use of sample data to generalize about a population. For this reason, the data used in a regression should be randomly selected, representative data from the population. In simple linear regression, one is estimating the parameters that define a line, slope and intercept. The equation for a regression line is represented in the form y is equal to b0 plus b1 times x. This may be familiar to you from simple algebra courses in which you learn y equals mx plus b, with m being the slope of the line and b being the y-intercept. In this case, b0 is the y-intercept and b1 is the slope of the line. The formula used to estimate b1 is shown. The parameters used to estimate b1 are the x and y values from a sample, of which the number of elements in the sample, n, is known. Once b1 has been estimated, b0, the y-intercept, can be estimated using the formula for a line by plugging in the mean of the x and the y elements in the sample. Let's look at an example. We'll walk through how to calculate a regression line and how to interpret the regression line systematically. Though we'll only be doing one example, you can re-watch this video to learn the system, which should apply in every case in which you have an x and y sample set and you'd like to calculate a simple linear regression line. Consider the following data set showing the relationship between a child's height and the average number of points he scores during a game in the basketball seasons in 7 consecutive years. The year is shown in the first row of the table. The student's height in inches, the dependent variable, is shown in the second row, and the number of points he scored in the corresponding year is shown in the third row. This is the y, or dependent variable. Let's first compute b1. b1 is equal to s sub xy divided by s sub xx. The equations are shown below. Let's break the equation down. First, calculate the various sums of x and y required to calculate the slope. In order to calculate the slope, or the sxy part of the slope, we need the sum of all the x values and the sum of all the y values. These are calculated here. The sum of all the x values is the sum of all the heights in inches, or 400 inches, and the sum of all the y values, or the average points scored, is the yellow value, 74.8. Now calculate the sum of the product of x and y. This is the sum of the products of the height in inches and the average number of points scored in the corresponding year. The sum of all of these products is 5,126.2. Next, calculate the sum of x squared. This is the sum of the height in inches for each year squared. Finally, you'll need to know the sum of x for the sxx equation, and this sum will be squared, so it will be 400 squared. Now plug all of these values in to calculate the slope. Sxy is equal to the sum of the products of x and y minus the sum of the x values times the sum of the y values divided by n, the sample size. We know that the sum of xy is equal to 5,126.2 from our table above, and we subtract the product of 400, the sum of x, and 74.8, the sum of y, and divide by n, the sample size, which is 6, because there are 6 years in question. So SXY is equal to 139.5. SXX is equal to the sum of the x values squared, which we know from above is equal to 26,788, minus the sum of x values, the sum of all the x values squared, or 400 squared, divided by n, which is 6. This is equal to 121.3. SXY divided by SXX is equal to beta 1, which is the slope of the line. So we divide 139.5 by 121.3 to obtain a slope of 1.15. We now know that B1 is equal to 1.15, so we can compute beta 0 based on this equation. Beta 0 is equal to the average of the y values minus beta 1 times the average of the x values. So calculate the average of the x values, which is 66.7, and the average of the y values, which is 12.5. Plug these values into the equation for beta naught and obtain 12.5, the average of the y values, minus 1.15, the slope of the line, or beta 1, times 66.7, the mean height over the course of the 6 years, and obtain beta naught equal to negative 64. So the regression equation is y is equal to 1.15x minus 64. Considering this data set and the regression equation, y is equal to 1.15x minus 64, what is the expected average number of points scored by the student when he is 70 inches tall? The range of heights of interest is 60 to 73 inches. So we would be interpolating for looking at a height of 70 inches tall. This is within the range of heights that were used to calculate the linear regression. So we plug the value of 70 in for the x value in the equation and find that the average number of points scored is equal to 1.15 times 70 minus 64, or 16.5. Thus, if the student is 70 inches tall, we would expect that he would score 16.5 points. What would we do if we were asking the same question about a student who's 7 inches tall? Remember that it's not a good idea to extrapolate a regression. This is because the regression line calculated is only value for the sample range. Outside of that range, it is possible that the relationship of the data is nonlinear, or better described by a different line, or even uncorrelated. In fact, because we have a negative value for our y-intercept, we can be pretty sure that for small values, the simple linear regression line wouldn't apply. It's not possible to get a negative number of points. In this case, any prediction outside of the range of 60 to 73 inches is extrapolation, so we cannot give an expected y value for the value of x equal to 7. This concludes our discussion of calculation of simple linear regression lines and how to interpret them. There are several practice problems in the question sets, as well as another example problem in Module 13. You can also rewatch this video to understand the system for calculating this line. If you follow the system for the practice problems in the sample set, you should be able to successfully calculate each of the linear regression lines you're discussing, as well as any other regression lines. Also note that you can learn to calculate regression lines using Excel or other online calculators. This can be a nice alternative to calculate regression lines for large sample sets. Hello, and welcome to this elementary statistics lesson on simple linear regression. In this lesson, you will learn the definition of simple linear regression, how to calculate a regression equation, and how to interpret a regression equation. Whereas correlation is not a measure of causal relationship,